purple indicates the CN. And the orange here denotes the A. Now, suppose we have some other sequence in the middle, right? That's the whole squeezing effect. Let's say the first value of the sequence is here. It looks a little bit confusing. I purposely kind of bumped it above the purple. That was intentional. Because if you look at this, if I were to say, is Bn contained completely in between An and Cn here, the answer would be no. It's not. Because do you see it kind of supersedes the purple for a little bit there. But if I were to continue this picture, and my intent with this picture is that from this point forward, the blue does always get sandwiched in between, do you see that there is some cutoff point after which the blue is always stuck in between the purple and the orange? That's what I mean right here. So it doesn't have to be contained from the very first element. It can be contained at some finite breakpoint later. You know, in this case, this is the capital N. But if this is the case for the rest of the terms, n going all the way out to infinity, then the squeeze theorem tells us that the one in the middle has to achieve the same limiting value as the outer limits. Daniel, you okay with that?
Sort of, yeah.
Okay, let me give you an example. Maybe that'll help. So how about let's take this for our generating series. The cosine of n over 2 raised to the n. I want to construct an argument to find the limit for this. Can anybody figure out what the limit is? What is the limit? Yeah, it's 0. Now here is an example where you may not want to convert to x's, right? I mean, you can do it if you try hard enough using some tricks. But the difficulty is if you just convert to x's, you see you're going to have trouble evaluating the cosine at infinity. And in fact, the only way to really do this in terms of x's is to use the squeeze theorem. So you might as well just use the sequence version of the squeeze theorem, right? Because ultimately that's where it's going to go anyway. So Daniel, coming up here, when we approach this problem, if I want to use the squeeze theorem, what I need to do is actually construct those bounding sequences, the AN and the CN. In other words, the one you're trying to evaluate the limit for is the one in the middle. So how do I start that process? Well, I just happen to see in the sequence that I have a cosine. And cosine is nice because it has a natural bound associated with it. What's the natural bound associated with a cosine?
Between 1 and
Between negative 1 and 1, right? So I'm going to start by just making an observation. Now, like I said, the one in the middle is the one we want for our sequence. So notice that we don't have what we want yet. We need that to be divided by 2 to the n. So what I can do is I can just multiply the inequality by 1 over 2 to the n. Notice if you look at the limit of the outer bounds, the 1 over 2 to the n and the negative 1 over 2 to the n. What is the limit as n goes to infinity of negative 1 over 2 to the n?
0.
0. Negative 1 divided by something infinitely huge. That's going to be 0. Likewise, do you see that's the same thing as the limit as n goes to infinity for 1 over 2 to the n? So by the squeeze theorem, it then guarantees us that the limit of the cosine of n over 2 to the n must also be 0. So by the squeeze theorem, more sense now?
Yeah, so it should equal the same thing, like the ones on the ends.
Yeah. The tricky part is when you use this, and I say the tricky part, I mean the majority of the problems you encounter that are like this will have a sine or a cosine in it. And it'll have something in the denominator that goes to 0. So I mean you can readily identify when it's relative. You guys saw this in the calc class, you know. The only kind of problems I gave you had a sine or a cosine, then it was multiplied with something which was positive. You know, so there's very much a common theme to all of this. I guess, yeah, I mean, I guess I should be more formal about that. Let me translate this into a more formal notation. So as far as the theorem goes, that's what I'm saying.
Only for 0?
Only for 0. Yeah, so it converges, I should say, to 0. A very simple little theorem, one which we'll use a couple of times, so I just want to mention it. You're really not going to do a lot of problems that utilize this, but I do want to illustrate to you why it's true. Work on our proof dynamics here. So how would I prove this statement? And what it says is that if you have a sequence and the limit of the absolute value of that sequence goes to 0, you're guaranteed the sequence without the absolute values also goes to 0. Well, looking at this, this is an if-then statement. How do I know it's an if-then statement? Well, you see that little implication arrow? So that's not just something that I use at random. I mean, that actually has mathematical meaning.
Well, which one?
The arrow.
Oh, yeah.
The arrow, yeah. See, this is how we phrase it in the English language. If A is true, then something else is true, right? So what I can do is I can put in here general statements, right? So if the statement A is true, then it follows that B is going to be true. The way we write that mathematically is A implies B. So when I use these little arrows in my lecture, it's not just something I'm making up. I mean, that's really what I'm saying. There's an implication that if the left-hand side is true, then the right-hand side must be true. And there's a lot that goes on here. You know, I'm not going to get into all the things that surround this. This is a big thing that's covered in logic and proof. But you can have statements which can be turned around, and you have statements which cannot be turned around. For example, if I say, if you're taking calculus 2, then you're taking a calculus 2 final. That statement makes sense if you turn it around. If you're taking a calculus 2 final, then you're taking calculus 2. So do you see how you can interchange the supposition and the conclusion and it still be a true statement, right? Whereas that example I'm sure I've given you before, all dogs have 4 legs. Well, assume for a moment all dogs have 4 legs, right? We don't have any 3-legged dogs named Lucky. What's that?
Dogs